Nice, lovely fourth degree polynomial here. Let's first identify all of our possible roots. So our constant at the end is 13, and our leading coefficient is 1. So we could have, well, what are the factors of 13? That'd be 1 and 13. And the factors of 1 are just 1. Okay, that's nice. So our possible roots would be plus or minus 1 over 1, which is 1, and 13 over 1, which is 13. Okay, so we have 4 choices. Well, that's really convenient because it's fourth degree. Okay, so unless there's something interesting going on here, this should be pretty quick. And then I want to set up my synthetic. So, start with x to the fourth, x cubed, x squared, x and constant. So we got a 1, a negative 6, 22, negative 30, and 13. And I'm going to be really lazy, and I'm just going to start with a 1 and see what happens. So we'll drop the 1, multiply to give me a 1. That's negative 5. Let's see. So that multiplies to negative 5. That would be 17. Multiplies to 17. Get negative 13 when I combine like terms. And I get negative, oh, look at that. We lucked out. I got a 0 on the first try. Okay. So I knew, because of that 0, that 1 is an actual root. Okay, so what does my factored form look like so far? So far it looks like x minus 1 as a factor. Okay. Now let's go back in, and since I'm not dissuaded, and honestly this time I want to show you that their multiplicities do exist, just to kind of make us a little nervous. Let's try 1 again and see what happens. So we drop the 1, multiply that, and we get negative 4. Multiply that, and I get 13, and multiply that, and I get 0 again. Okay, so what does that mean? That means 1 shows up as a factor twice. Okay, and then what do the remaining numbers tell us? The remaining numbers, let's see. So I did synthetic twice, so that's not x to the fourth anymore, that's x squared. So that's x squared minus 4x plus 13. And at that point, now that it's quadratic, we can try to look at if it's factorable, and if you want to take a second sort of think about that. It's actually not. There's no way factors of 13 will give us a 4. So in order to find the zeros, since we already know that 1 shows up twice, so it has what's called a multiplicity of 2, then there's got to be some other, 2 other zeros of some flavor. So I'm going to come over here and we'll solve for that quadratic and see what we get. Okay, so we get a equals 1, b equals negative 4, and c equals 13. So x equals a negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so let's fill in our numbers then. So that would be a negative 4, 1 and 13, and that's 2 times 1. All right, so we get 4 plus or minus 16 minus 4 times 13, which is 52 over 2. And that's 4 plus or minus the square root of negative 36 over 2. Okay, so the fact that a negative showed up tells us that we have some sort of imaginary solutions then. So that would be 4 plus or minus 6i over 2. And each of those is divisible by 2. So I get 2 plus or minus 3i. Okay, so those are our 2 other solutions. So 2 plus or minus 3i. Okay, and so those are perfectly fine answers. So one common concern that I hear from students whenever they're learning rational roots theorem is they get a little nervous when there's lots of choices. And they start asking themselves, well, how do I know which number is the correct number to test and use? And the answer is you just practice. You just keep doing it over and over again. But there are some techniques that will narrow down the options. And so this is where I'm going to show you something called Descartes' rule of sign. Is a nice, easy technique to apply, and it does potentially narrow down our list of possible rational zeros to a somewhat smaller list. And again, it's not too bad a technique to throw in there. So to narrow down the list of possible zeros, we're going to use something called Descartes. Let me switch to a different color. Sorry. Descartes' rule of signs, which will list the possible number of positive and negative real zeros. Note that real zeros include both rational and irrational zeros. Okay, so in other words, Descartes' rule of sign, what it's going to do for us, it's going to give us an idea of how many positive or negative solutions there are. And when you have like 10 choices and half are positive and half are negative, and you know there's more positive than negative, that sort of tells you where you should start guessing. So it does sort of help narrow down options. Okay, so to find the number of positive solutions, what we're going to do is we're going to count the number of sign changes in the original function of f of x. So the number of positive real zeros is equal to the number of sign changes of f of x, or less an even integer. Okay, so this sounds a little confusing to say, but we'll kind of look at this first illustration. I'll kind of point out that that's what this was really trying to tell us. Okay, so looking at f of x, it starts off from positive to the next number is negative, right? So there's a sign change. Then it goes from negative 6 to positive 22, so there's a sign change. It goes from positive 22 to negative 30, there's a sign change. And from negative 30 up till 13. So how many sign changes were there? We changed signs 4 times, so there's 4 sign changes. Okay, which means, and this is what this is trying to say with this, the number of positive real zeros is equal to the number of sign changes or less an even number. That means there could be 4 positive solutions or 2 positive solutions. So we're just going to go down an even amount from there. Okay. How many total solutions are there, though? So if you kind of look at it, it's a 4th degree polynomial, which means it could cross the x-axis 4 times. And I've got a good evidence that it could mostly be positive. So that kind of tells me that I should hang out with the positive numbers when I am doing my rational roots theorem. Okay, there's a similar process for negative, and I say similar in that we have to evaluate the function first, and then we can do this sort of analysis. So we're going to find f of negative x, and then we're going to count the sign changes of f of negative x. So once we evaluate it at a negative, then we'll count whether it switches from positive to negative, and that'll give us a clue. So the number of negative real zeros is equal to the number of sign changes of f of negative s, or less an even integer. So same issue as before in that it's either going to be, like in the positive case, there were 4 sign changes, so either 4 or 2. So this is the same thing. So whatever number of sign changes I get, it could be an even number less than that. So let's first evaluate negative x then. So I'll kind of do this, replace this. Squared minus 30 times negative x plus 13. Okay, now some of that we can simplify down. So f of negative x, if you take a negative to the fourth, you get x to the fourth. That negative x cubed becomes a negative, so a negative times a negative is positive, so plus 6x cubed. Plus that negative squared is still going to be positive, so plus 22x squared. Negative times a negative is a positive, so plus 30x plus 13. Okay, so when we evaluated at the negative, those were the terms we got. And so let's kind of look real quick at how many sign changes there are. And notice that's positive, 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 positive. So there's no sign changes. Okay. So no sign changes, which tells me that there are 0 negative real zeros. Okay. So before we attack a problem like this, it's a nice, real quick sort of gives us a hint as to what to look at. And let me kind of go back to the problem we worked out earlier with the multiplicity. Notice it's the exact same problem, same function. And using Descartes' rule of sign, we already figured out that there's 0 negative zero solutions, and there's either 4 or 2 positive. So when I come back up here, what did we notice? We plugged a 1 in, so we plugged in a positive number, and we found that it was twice. Okay, so Descartes, right, he's dead on. And then we found that the other 2 solutions happened to have been imaginary, and Descartes' rule of sign said that. So it said you're either going to have 4 positive real solutions or 2 positive real solutions, and obviously if they're not real, they have to be imaginary. Okay, so Descartes' rule of sign is useful in that it helps us organize our thoughts and sort of be smarter about how we're picking numbers, and then lets us sort of analyze our answer and say, oh yeah, it does kind of fit that particular pattern. So let's kind of practice the rule of sign just on this example, and then we'll kind of jump in and look at some actual putting rational roots together with Descartes' rule of sign and sort of map out a somewhat decent process. So let's start with analyzing the positive solutions. So we notice we go from a negative 2 to a positive x, and a positive x to a negative x, and a negative x to a positive 7. So we had 3 sign changes. So as far as positive roots go, we know there's either 3 or 1 positive real roots. Okay. Then we'll look at f of negative x. So we'll evaluate that at negative x there, where all the x's are. Okay, so we'll simplify that. So if I take a negative and I cube it, that means the negative comes out, and a negative times a negative is a positive, so I get positive 2x cubed. That negative x squared is going to become positive, so that minus is still going to be there on the squared term. Negative times a negative is a positive, and then plus 7. All right, how many sign changes do we got here? So we have 1 and 2. Okay, so we have 2 sign changes and evaluated at negative x, which means we have 2 real roots that are negative. Okay, so if I was going to use a rational roots theorem on this particular example, and I had, 6 numbers, 3 were positive, 3 were negative, because I know for a fact that there's 2 negative roots and I've got either 3 or 1, I'd probably start plugging in negative numbers just in case, because I know I'm going to get 2 that are going to work. Versus the positive case, it could be all 3 or it could be 1. So anyway, so sort of how that logic works on that.